Okay, good morning, gang. So, before we get started, I just want to say one or two things, and then we'll jump right in. Where am I going? I'm looking for this stuff. Yeah, stuff. Who is missing here? Let's actually look at the grades. Oh, that was the other thing I needed to do. Yeah, I'm so stupid. Okay. Okay. Oh. That's that. And this is this. Okay. So today I would like to talk about antiderivatives. I guess I can do this. Yeah. All right. Oh, I need to close this before I switch back to the shared on. Everybody wants to see everybody's grades. Okay, so I do have two people who haven't taken the second exam yet. I think one of those people I've had a conversation with and made arrangements. It also looks like he's not here. Actually, neither of them are here. All right, so I guess I don't need to have that conversation with you guys. I'll just reach out to them via email, cross my fingers, and hope they reply. Then we're ready to go. We're ready to jump in. The only announcements I had are for folks who are not here anyway. So there's a few things that I wanted to talk about today. I know that the sigma summation notation that we introduced last time with the Riemann sums can be a little bit intimidating. So I would be happy to revisit that a little bit, but I want to do it in a way that is relevant to the work we're doing. I'd also like to talk about antiderivatives and then the definite integral. So those are the two big things here today. Okay, so antiderivatives and the definite integral. Oh, that's a black pen. Let's go. Black refilling it. So antiderivatives are actually coming from section 4.9, which is not an official part of the curriculum here, but I cannot not talk about them because you're going to need them in section 5.2. So that's the first topic. Before we do this though, a homework problem or two. So let's take a look at your homework and we can grab one or two out there. Are there any preferences from you guys? Damon requests number 3. Any other strong feelings about which homework problems we would like to see as an example? The Riemann sum stuff before we get started on the new material. So one of these does have the right and left endpoints. I'm sorry, this is just because I wanted to make sure there was one where you had to like look at the pictures, and all of those had both right and left endpoint stuff, but I don't think you'll have any hard time. Yeah, number 3, this is actually the one I was thinking of, so I would be happy to do this. Are there any other strong feelings about what you guys would like to see here? So express the area under x equals x squared plus the square root 1 plus 2x. 5 is less than equal to x less than equal to 7. As a limit. Do not evaluate. Three and 9. Okay, 3 and 9 it is. So here is number 3. They tell us to express the area underneath this function from 5 to 7 as a limit. I'm not sure what the graph of this function looks like. I'm really not. So I'm not going to bother drawing a picture here. But remember the way we play this game. So what we need is the limit as n goes to infinity, sigma I equals 1 to n, f of xi times delta x. This is the limit they're asking for. I think in the WebAssign they use a little n. So I'll swap the big N to a little n at the end. I might as well do it now. Why not? They are using little n's, right? Yeah, okay. So the game here is to just plug in for these guys, right? Delta x is always b minus a over n. Again, they're using a little n here, so I'll use a little n here. This is b, this is a. So that's 7 minus 5 over n, which is 2 over n. And we calculate delta x first because xi involves delta x. So if I want xi, for a right-hand Riemann sum, that is a plus I times delta x, which is 5 plus I times 2 over n, because a is 5 and delta x is 2 over n. So then what is f of xi? Well, f of anything is what you get when you plug that thing in for x in this formula. So f of xi is xi squared plus the square root of 1 plus 2xi. So now that I have all these things, I just need to plug them into my formula. So the area under f of x from x equals 5 to x equals 7, this is the limit as n goes to infinity of the sum from I equals 1 to n f of xi, and I'm going to put all of this in parentheses because I'm going to multiply it by delta x. Five plus I times 2 over n all squared plus the square root of 1 plus 2 times 5 plus, oh, did I swap the 2 and the I here? I'm sorry. This should be an I and this should be a 2, sorry. Yeah, I times 2 over n. Sorry about that. Okay. All right. And then close this bracket, and then I need to tack on my delta x, which is 2 over n. So I suppose it would be nice to get this all in one line. That's lim n to infinity. I'll do a little bit of simplification here. Sum I from 1 to n, bracket 5 plus 2I over n all squared plus the square root of 1 plus 2 times 5 plus 2I over n. So this is the f of xi piece, and then I slap on my delta x, which is 2 over n.
I put that this morning in WebAssign, and I got it wrong. Maybe it's because of the brackets there. I'm not sure. Let me try something again.
You will need, yeah, you'll need parentheses around this object. If you put it in without the parens or brackets or some delimiters around this object, without those, it's not correct.
Okay, that makes more sense, because I was like, what the heck? I know that this has got to be it.
I understand how frustrating that could be. Yeah, the thing to remember is that this piece right here is multiplying this piece right here. So if this guy happens to be made up of more than one chunk separated by addition or subtraction, you will need parentheses around him. It sounds funny, but this is actually something I have a hard time getting Calc 2 students to do. They have, like, for whatever reason, we don't do it in this setting, we do it with integrals, but for whatever reason, they never want to put this shit in parentheses. And I'm always telling them, you got to do it. And then on exam 1, I'm always taking off a half point. But yeah, so if you entered this just without brackets or parens, it would technically be wrong. And that's probably why WebAssign's giving you a hard time, but this is for sure correct. And the reason they tell you not to evaluate the limit is because we can't, right? There are some things we could do to try and split this sum up and manage it, but because of this square root piece here, there's nothing we could really do nice with this. So if I wanted to evaluate this limit, I would distribute this 2 over n to this piece and to this piece. Then I would FOIL this piece out, and then I would split up my sum. Each piece would get his own sigma thing, and I would do my best to try and evaluate each sum, but the piece that ends up with this guy, I wouldn't be able to handle. This piece I actually would be able to handle just fine. He's not bad. But this piece I wouldn't be able to handle because I don't have any formula for the sum of a square root of a bunch of stuff. Let's take a look at that other one. So I think we wanted to see number 9 as well. Yeah, find the most general antiderivative. Okay, so this is something we haven't talked about. This is something we're talking about for the first time today. I'd be happy to work this problem as an introduction to antiderivatives. So let me, before I do number 9, let me give you the basic idea of what an antiderivative is, since we haven't mentioned it in class yet. You can actually think of differentiation as a ladder. Like you can go up or you can go down. You can go forwards or you can go backwards along the differentiation chain. We know that f prime is the derivative of f, right? Well, if I give you a function f, the question of antiderivatives is, can you find a function who has f as its derivative? Yeah, kind of, Tenzina, and this is the attitude that Santa Fe takes, is that you'll learn antiderivatives in section 5.4, but that's really a shitty way to think about it because you need to have the concept of an antiderivative to understand the fundamental theorem of calculus, which is supposed to come before we talk about section 5.4. So the order is a little bit wonky unless we have at least a brief discussion of antiderivatives. There's a slight change when you talk about indefinite integrals, meaning that the question of finding an antiderivative versus finding all the antiderivatives. But yes, indefinite integrals are antiderivatives. That is true, or at least the problem of solving an indefinite integral is equivalent to finding an antiderivative. So really quick, for those who don't know, given a function little f, an antiderivative and I'm using the indefinite article an here because there's more than one for little f, is another function. We usually use the symbol capital F such that the derivative of capital F prime, is equal to little f. This is the definition of an antiderivative. So you're trying to undo differentiation, right? You can take a derivative to go forwards on the differentiation chain, and you can take an antiderivative to go backwards on the differentiation chain. So some examples. If f of x is 2x, can I think of anybody who has 2x as his derivative? I think of someone who I can differentiate to get the function 2x. We think for a minute, we're like, oh shit, well I've seen a lot of stuff like that. I know when I differentiate a polynomial or a power function, I bring the power down and reduce the power by 1. So Angelica, any thoughts here? Sorry, I saw your window light up like you were about to say something. Imagine that this came from taking a derivative. Yeah, very good. Zach's got it in chat. So an antiderivative would be x squared. All right, if I differentiate this guy, I get this guy. I would bring the power down and reduce the power by 1. That would give me 2x. I'm going to talk about most general antiderivatives in a second, but for now I just want to prime the idea, forgive the joke, before we talk about the more general thing. Okay, how about this? And t, sorry. Who can help me with an antiderivative for e to the x? Who can I differentiate so that the derivative is e to the x? Yeah, Carl's got it, e to the x, right? When you differentiate e to the x, he doesn't change. He stays e to the x. Right? So if I differentiate e to the x, I get e to the x. Therefore, capital F of x equals e to the x is an antiderivative for little f equals e to the x, because the derivative of big F is little f. Just like the derivative of x squared is 2x. And Tanzina in chat is adding this plus c. I'll explain the plus c stuff to you guys in just 1 second. I'd like to do one more example. Okay, what about secant squared? What if little f is secant squared? Who could I differentiate to get secant squared? What is an antiderivative for secant squared? Who has secant squared as his derivative? Yeah, good, tangent x. Okay. So I'm hoping that we're starting to get the basic idea for what an antiderivative is. Essentially, you have to think about all of your differentiation rules and all of your differentiation processes and ask, yeah, who can I, if I run differentiation backwards, what do I get? Or who could I differentiate in order to get the given thing? Which means you have to be really good at differentiation to even have a hope at finding antiderivatives. Now, thankfully, you guys have all been practicing differentiation for about 2 months, so we should be really good at it. if capital F primed of x equals little f of x, then for any constant capital C, capital F plus C primed is also little f. So this is, this theorem here is trying to explain or explains this concept of a more general antiderivative. It's true that x squared differentiates to 2x, but so does x squared plus 1, x squared minus 5, x squared plus pi. If you added any constant here, you would also have something that differentiates to 2x. The proof of the theorem is trivial. F of x plus c all primed is equal to d dx f of x plus c, which is d dx f of x plus d dx of c. d dx of c is 0. d dx of f of x is capital F primed of x. I'll continue this down here. This is capital F primed of x plus 0. Capital F primed is little f, and 0 is 0. So if I ask you for a most general antiderivative, then we usually add on a plus c to whatever the fundamental or base or obvious antiderivative is. So for example here, if little f is 2x, then the most general antiderivative is capital F equals x squared plus c, where c is, and the word we use is arbitrary constant. Because not only x squared differentiates to 2x, but x squared plus 5 also differentiates to 2x. X squared minus 7 also differentiates to 2x. X squared plus any constant differentiates to 2x because the constant piece differentiates to 0. So now let's return to that problem from the homework, problem 9, and see if we can find the most general antiderivative for 2/5 minus 9 over x, with the understanding that x is positive. Before I leave this page, any questions on what an antiderivative is, these examples, or the plus c thing? Going once? Going twice? Yeah, yeah. Go ahead.
Could I take a picture of the last page, please?
The page before this?
Yes, sir. Thank you so much.
Of course. Okay, any questions on this before we move on? So to find the most general antiderivative, first you find an antiderivative, and then you tack on a plus c. So let's return to the example from the homework, example 9. Find the most general antiderivative for f of x equals 5/2 minus 9 over x, where x is understood to be positive. Now for the process of finding antiderivatives or thinking about antiderivatives, we don't really need this. This is here for technical reasons that will become clear after we've solved the problem. So for now, forget about this part. Just think about this. I need to find an antiderivative for 5/2 minus 9 over x. So I need to find something that differentiates to 5/2, and I need to find something that differentiates to 9 over x, and then I will subtract those two things. Think of the 5/2 here as just being like a number, right? So what sort of functions can I differentiate? Who has a constant derivative?
Anything to the, x to the first power.
Yeah, anything that has an x to the 1, right? So I'd say recall that the derivative of mx is just m. So an antiderivative for m is mx. So the antiderivative for 5/2 is going to be 5/2 times x. Now for the 9 over x piece, all right, I'll just write it like this so it's clear, right? This is the antiderivative for this. The minus is going to come along for the ride. And then I need to find an antiderivative for 9 over x. And for that, do another little recall. Just some algebra. 9 over x is the same as 1 over 9. Same as 9 times 1 over x. So who differentiates to 1 over x?
Natural log.
Good. And ln x primed equals 1 over x. So 9 times ln x primed equals 9 times 1 over x. So the question mark stuff there is going to be the natural log, because the derivative of 9 times natural log x is 9 times 1 over x, and that's the same as 9 over x. Okay, so we've got these two kind of little side work bits. So f of x, capital F of x, my antiderivative is 5/2 x minus 9 times the natural log of x. And then in order to get the most general antiderivative, I tack on a plus c, because I could have like a +5 or a -2 or a +10 here, and it wouldn't change the derivative. The derivative would still be this. Can anybody explain to me why they say x has to be greater than 0 now that we've solved the problem?
Because it would be undefined.
Good. The natural log function isn't defined if x is not greater than 0. Remember, the domain of the natural log is just positive real numbers. So if x were not greater than 0, this would not actually be an antiderivative for this. There is a way to get around this, and it involves using absolute values, but you still have to stay away from 0 itself, and we'll talk about that in just a second. So I think your textbook gives the table here in 4.9. If they wait until 5.3, then I'll wait until 5.3, but I'm pretty sure there's this table here, and I'd like to show it to you as soon as I can because it's useful. Yeah, so here are some basic anti-differentiation rules. Some functions that we all know and love, and some antiderivatives. So, if capital F primed of x equals little f, and capital G primed of x equals little g, then function and antiderivative. So if your original function is c times little f, then an antiderivative here would be c times big F, because when you differentiate this guy, the c just comes along for the ride because he's multiplying. Actually, let me use a different symbol here because we're using c for the constant that we add on at the end. So I'll use k for my little multiplicative constant. And then your general antiderivative would be this, k capital F plus c. And then if you had a sum of two functions, sum or difference of two functions, f plus or minus g, then your antiderivative would be capital F plus capital G, or if it was a minus, it would be capital F minus capital G. And then to get your most general antiderivative, you would slap on a plus c. This next one is called the power rule. So if you have some power of x and you want to find an antiderivative, think about how you would differentiate. Normally you differentiate by bringing the power down and then reducing the power by 1. So who would differentiate to have the power x to the n? Well, it has to be a power greater than that by 1. But then if I differentiate this, I'll bring down the n plus 1 and then reduce the power by 1. So in order to get rid of the n plus 1 that comes down, I have to divide by n plus 1. And then you'd tack on your plus c. E to the x is, of course, its own antiderivative and derivative, and any constant times e to the x works the same way. Is there anything else in this table that I'm missing? I think that's enough to get you started at least. Yeah, this is good. Let's continue. There's a few other important antiderivatives that I want to talk about. So other basic antiderivatives that you should know are the antiderivatives for trig functions and inverse trig functions. So I'm continuing the table here. So a constant times any function, his antiderivative, the multiplicative constant, comes along for the ride, antiderivative plus c. Sums and differences of functions, you can split up antidifferentiation over addition and subtraction, just like you can for regular differentiation. Powers, this is probably the most important one, at least as you're getting started, because we use this rule all the time. To antiderive a power function, you add 1 to that power and then divide by that new power. A quick note, this only works if n is not equal to -1. Because if n is -1, then you're looking at 1 over x, whose antiderivative is the natural log of x. And if we want to be as general as possible, we'll say the natural log of the absolute value of x. And that's to do with that domain of the natural log thing. This works as long, so my most general antiderivative would be ln absolute x plus c, and this is where x is not equal to 0. Your trig functions, an antiderivative for cos x, who differentiates to cos x? Oh, that's sine x. An antiderivative for sine x. Well, if I differentiate cosine, I get negative sine. So if I want to anti-differentiate sine, that's going to be negative cosine. And then we add on our plus c. Tangent is a little bit more complicated. We're not ready for tangent or for secant. But secant tangent and secant squared we can do. We know that the derivative of tangent is secant squared, so an antiderivative for secant squared is tangent. And we know that the derivative of secant is secant tangent, so an antiderivative for secant times tangent is secant. And as long as you're putting these things in your notes, I'm going to give you just a couple more. Who differentiates to 1 over 1 plus x squared? Might seem strange to see that showing up in the trig stuff, but I promise you it's something triggy.
Is it tangent squared of x?
Not tan squared. It's an inverse trig function. This is arctan, or tan inverse. This is AKA, if you prefer the other notation, arctan x. Remember the derivative of arctan is 1 over 1 plus x squared. That was something we got using implicit differentiation. Yeah, very good. Miranda's got it. Miranda and Zach. Good, good, good. Okay. How about this one? One over the square root of 1 minus x squared. I want to pause for a second. So Tanzina asked a really good question in chat about this last guy. Could I call this the natural log of 1 plus x squared? The answer to that is no. And that's because of the chain rule. So in a second, Tanzina, I want to finish this table with this last one here, and then I'll give you a nice thorough answer to that question. But the short answer is no. So does anybody remember who has the derivative almost inverse sine? Yeah, arc sine or sine inverse, AKA arc sine x. Negative 1 over square root 1 minus x squared, that's inverse cosine. Okay. So a quick comment, answer to a question. This is AKA arc cos x plus c. So there's a really good question there. Is ln 1 plus x squared an antiderivative for tan inverse x? In other words, if I differentiate this, do I get this? Oh no, I said that wrong, I'm sorry. Do I get the same as I get when I differentiate arctan? Let me say this another way, sorry. Sorry. So the question is ln 1 plus x squared an antiderivative, not for arctan, but for 1 over 1 plus x squared. That was the question. I'm sorry. I wrote it down wrong. Yeah. So is the ln of 1 plus x squared an antiderivative for 1 over 1 plus x squared? It's tempting, right? Because ln x differentiates to 1 over x. What about ln of 1 plus x squared? Shouldn't that differentiate to 1 over 1 plus x squared? But the answer here is no, and it's because of the chain rule. The derivative of ln 1 plus x squared does involve 1 over 1 plus x squared, but then by the chain rule, you have to multiply by the derivative of 1 plus x squared. Remember, the derivative of the natural log of some stuff is 1 over that stuff times the derivative of that stuff, or 1 over u times u primed. So this would be 1 over 1 plus x squared times 2x, or 2x over 1 plus x squared. And the more general question that we're often tempted to ask in this setting is, well, what about 1 over some function? Does that ever have the antiderivative ln of that function? And the answer to that is no. Only if that function is linear do you get something like that. So I'll say it like this. It's a common mistake. It's actually a true-false question on my first test in Calc 2, almost always. More generally, yes, and even in the case of linear functions, it's not super straightforward. Normally I write this in terms of integrals, is ln f of x an antiderivative for 1 over f of x? And the answer here is no. If f of x is like mx, then 1 over f of x is 1 over mx is 1 over m times 1 over x. We'll have antiderivative capital F of x equals 1 over m times the natural log of the absolute value of x plus c, but for any other f, but not for any other functions, little f. And I really shouldn't be using the capital F here because that's confusing the notation. But if you want to find an antiderivative for 1 over some shit, then you're only ever going to get a natural log if you can write that as just straight 1 over x. That's the safe way to remember. Only 1 over x has antiderivative natural log x. In general, 1 over f will not antiderive to natural log of f. So we'll be able to talk about this a little bit more when we talk about section 5.5 next week, which is on the substitution rule for integrals, which is like a backwards chain rule. So you're going to get a backwards version of most of your differentiation rules. And the backwards chain rule is the last thing we learn in this class. And I'll be able to give a much better answer in terms of integrals then. But for now, I'll ask you to believe me that due to the chain rule, right, watch this. If you differentiate the natural log of some shit, you don't just get 1 over that shit. You get 1 over that shit times the derivative of that shit. And this piece messes up that thing that Tenzina is asking, and that most people are tempted to do. The best answer I can give to this is that if little f is linear, then 1 over little f's antiderivative will involve the natural log. But to give a really thorough answer to that question, we'll need what's called the substitution rule, and we don't have that yet. So for now, I'm going to put a pin in it. And remember these antiderivatives. Remember the antiderivatives that I gave you. And as we want to find other antiderivatives, check your work. If you're tempted to say that this should be an antiderivative for 1 over 1 plus x squared, check. You can always check, because you can always differentiate the thing you think is an antiderivative and see if you get what you should out. The derivative there is not 1 over 1 plus x squared, it's 2x over 1 plus x squared. And you can always do this little check. Okay. So those are antiderivatives. That power rule is super useful. I'd like to do one more example, and then let's see. Yeah, let's do something like number 12. So particle is moving on a straight line. With the acceleration a of t being 2t plus 7. And then they don't give me the original, they don't give me the position function or the velocity function. They just tell me the starting position and starting velocity. So you can think of this particle as living on a straight line. When time is 0, so I'll put position 0 over here. At the starting moment, he's out here at 6. This is where my particle starts. His starting velocity is -2, so he's going backwards. But his acceleration is positive, 2t plus 7. So he's going to be going backwards at the start, but he's going to be slowing down, and then he's going to want to turn around. They want to find the function s of t. So the trick to this is to remember the derivative of s is v. The derivative of your position is your velocity, and the derivative of velocity is acceleration. So v is an antiderivative for a, and s is an antiderivative for v. So they're starting us down here at the bottom of the differentiation chain with acceleration. We're going to have to go up twice. We're going to go up from a once to get v, and then we're going to go up from v once to get s. So what is v of t? My velocity function is an antiderivative for a. So I apply my power rule here. That's 2 times, what's the power rule say? It says if I want to anti-differentiate t, I add 1 to the power, and then I divide by the new power. So this is t to the 1. So 1 plus 1 is 2. So my new power is 2. And then I must divide by that new power. And then an antiderivative for the constant 7 is 7t. And then I have to add on my plus c. I can simplify a little bit. The 2's cancel. We already know that the antiderivative of 2t is t squared. So the antiderivative for a is t squared plus 7t, and then I've got my plus c here. Before I go and try to figure out s from this by taking another antiderivative, I would like to find this constant c, because this particle is only doing one thing. And that's where this information comes in. So I can use the fact that v of 0 is -2 to find c. V of 0 is 0 squared plus 7 times 0 plus c. But v of 0 is supposed to be -2, so -2 is 0 squared plus 7 times 0 plus c. In other words, -2 is c. So v of t is really t squared plus 7t minus 2. So that's my velocity function. And if I want to find position, I need to antiderive again. S of t is the antiderivative for v of t. So if I want to antiderive t squared, again, I add 1 to the power and divide by the new power. So that will be t cubed over 3 plus 7 times, if I want to antiderive t to the 1, I add 1 to the power and divide by the new power. That's t squared over 2. So this is all coming from that power rule, right? Antiderivative of x to the n is x to the n plus 1 over n plus 1. So an antiderivative of t squared is t to the 2 plus 1 divided by 2 plus 1. That's t cubed over 3. Antiderivative for t to the 1 is t to the 1 plus 1 over 1 plus 1. That's t squared over 2. And the plus and the 7 come along for a ride according to the first rows of our antiderivative table. And then the minus 2, he differentiates to minus 2t. And I need to add on another constant here. So let me call this like c2, because it's some other constant. Now I use the information they gave me about s. S of 0 is 6. To find c2. On the one hand, s of 0 is 0 cubed over 3 plus 7 times 0 squared over 2 minus 2 times 0 plus c2. On the other hand, s of 0 is 6. So 6 is 0 plus 0 minus 0 plus c2. In other words, c2 is 6. So finally, s of t, I just come back to my formula for s and I plug in for the constant c2. It's t cubed over 3 plus 7t squared over 2 minus 2t plus 6. So you use the fact that velocity is the derivative of position and the fact that acceleration is the derivative of velocity. So I start here by antideriving the acceleration to get the velocity, and then I plug in the information they gave me to solve for the constant. That gives me my velocity function with no arbitrary constants. I know for sure exactly what that function is. Then I antiderive my velocity to get my position. But oops, that gives me another arbitrary constant. But since they told me the initial position, just like they told me the initial velocity, I can use the initial position to solve for that constant. I plug in 0 because they said S of 0 is 6, so I plug 0 in everywhere for t, and I know that that should be equal to 6. So S of 0 is 6, but S of 0 is also C2, so C2 has to be 6. And that gives me my position function. Tanzina asked if we could also do number 11. I don't want to compromise time too much, so I can move quickly and take a short look at number 11, but I do want to introduce the notation for definite integrals. For number 11, they're asking you to do the same sort of thing. Find an antiderivative, and then they give you f of pi over 4 to help you solve for the constant. So they tell you f primed of t is secant t times secant t plus tangent t, which is secant squared t plus secant t tangent t. So f itself, the antiderivative for f primed, antiderivative for secant squared is tangent. Antiderivative for secant tangent is secant. And then you tack on a plus c. Now they also gave you some other information. They told you that t is bounded between negative pi over 2 and pi over 2. That's all well and good. They also told you that f of pi over 4 is negative 2. So they also said f of pi over 4 is negative 2. So if you plug in pi over 4, you get tan pi over 4 plus secant pi over 4 plus c. We know that this should be equal to negative 2. The tangent of pi over 4 is 1. The secant of pi over 4 is the square root of 2. And c is c. So then I subtract 1, subtract root 2, and then I plug back in here. So f of t is tangent t plus secant t plus negative 3 minus root 2. So I could write that now, plus negative 3 minus square root of 2. All right. I know that was quick. We got some other things we need to get to, but I didn't want to leave you hanging on it. These are called initial value problems, where you're given the derivative and some information about the original function, a point on the original graph. You take your antiderivative, and then you plug in the information they gave you to solve for the constant. So it's the same sort of thing we did in the last problem with the acceleration and position. So run through these on your own. I don't think you'll have a terribly hard time as long as you're patient. And remember, first just solve what you know, solve for the antiderivative, and then look and see what's left. What else could you do? What else might they want? So now I want to return to area problems. In particular, I want to talk about, section 5.2. So the exact area that we've been talking about has a special name. It's called the definite integral. We don't need to go through the careful definition there because deltas and epsilons don't mean anything to us, but we've got some meaningful stuff, some bullshit, lots of Riemann sums. Okay, so notation, that's the big thing here. We're just learning notation. So this is section 5.1. Or sorry, no, it's not. This is section 5.2, the definite integral. This is going to make up the first third of Calc 2, right? For some people, the first half of Calc 2. It depends on the professor. If f of x is positive on the interval a, b, and has no infinite discontinuities, then the area bounded between the graph of f and the x-axis is called the definite integral of f from a to b. It's denoted, or it's written as, this is a big long S. You put the littler number down here and the bigger number up here. F of x dx. And every symbol here has meaning. You cannot skip any of them. And we've seen in the previous section that this area is the limit, as your book uses little n's, so I'll use little n's, sigma I from 1 to n, so limit n to infinity, sigma I from 1 to n, f of xi times delta x. So you have some problems in your homework that ask you to write this integral as this limit, or ask you to write this limit as an integral. This definition is what allows you to do it. And remember that both are just ways of saying the area bounded by that function on the interval AB. That's the idea. There are a bunch of rules for these integrals that will allow us to manipulate them, pull them apart, put them together. I want to introduce them in the order your textbook introduces them, and I don't want to scare the shit out of you, so there's that stuff. I guess the first thing we need to talk about is what happens if f is not positive everywhere. Don't care about the midpoint rule, swapping signs, linearity, additivity, comparisons. All right, that's it. All right. So quick note. If f is not positive, everywhere on AB, then the definite integral measures what's called the signed area bounded by f. So what am I talking about there? Well, maybe my graph looks like this. So maybe f spends sometimes up above the x-axis and sometimes down below the x-axis. Maybe A is here and B is here. So I'll call this area A1, I'll call this area A2. This is A1, this is A2. So then the integral here from A to B of f of x dx, areas are positive, right? But here some of this area is below the x-axis, some of this area is above the x-axis. So this would be A1 minus A2. So the stuff that's below the x-axis gets counted with a negative weight. And the stuff that's above the x-axis gets counted with a positive weight. So over here, I guess I just call this A if you're looking for some consistent notation. This is the first little thing we learn how to deal with integrals. So the integral from A to B of a positive function is just the area between that function and the x-axis. But if that function isn't positive everywhere, if some of it is negative and some of it is positive, then whatever area is beneath the x-axis gets counted with a negative weight. And whatever area is above the x-axis gets counted with a positive weight. And the term for this is signed area. So I think of this as negative area and this as positive area. This makes sense? Any questions about this? So for example, let's calculate the integral from negative pi over 2 to pi over 2 of sine x dx. I know that this is the signed area bounded by f of x equals sine x from negative pi over 2 to pi over 2. So let's look at the graph of the sine function. See if we can't get a feel for the area we're measuring. I know over here, sine x, if this is like 1, I'll call this like pi. Sine of pi is 0. Sine of pi over 2 is 1. And I know that the sine function here looks like this. It's this wave, right? And he continues over here like that. On the other hand, over here on this side, well, negative pi, so this is negative pi over 2. It's negative 1. Over here, the sine function looks like this. So the area I'm looking for from negative pi over 2 to pi over 2 is this. Okay, so what is this integral? Well, it's this area counted with a positive weight plus this area counted with a negative weight. But by the symmetry of the graph, even though I don't know what those areas are exactly, I know that this is the same size as this, but this should be negative. So if I call this area A1, and I call this area A2, I know that A1 is equal to A2 by the symmetry of the graph, and because A1 is below the x-axis, it is measured as being negative by the integral. I said by the integral. So what is the value of this integral?
Is it 0?
Yeah, exactly, right? And this is like 5. This is like -5. -5 plus 5 is 0. So therefore, the integral from -pi/2 to pi/2 of sine x dx is equal to -a1 plus a2, which is 0, because a1 equals a2 by symmetry. And there's a more general rule that we can deduce from this, but first I'd like to take any questions you have on why this integral is 0. Is it clear what's going on here? Area above the x-axis is measured as positive. Area beneath the x-axis is measured as negative. These two areas are the same, but one is above and one is below. So when you add them up and you ask what's the total area there, you've got like -2 plus +2. This guy is like -2, this guy is like +2. And it's not actually 2. I don't really care what the area is. All that matters is that they're the same size and one is negative. So when you add them, you get 0. I will get you to a place where we can calculate this area exactly very soon, but we're not quite there yet. We need what's called the fundamental theorem of calculus to do that. And I'll get you that early next week, I think. The more general result I'll actually call a theorem. If f of x is an odd function continuous on the interval -a to a, then the integral from -a to a of f of x dx is always 0. What made this work was the symmetry, right? And any odd function will have this same symmetry. So remember what odd functions are. They're functions whose graphs are symmetric about the origin. And what made this work is the fact that the graph was symmetric about the origin. This is an important rule that you need to remember. There's a similar rule for even functions. If f of x is an even function continuous on the interval -a to a, then the integral from -a to a of f of x dx is equal to 2 times the integral from 0 to a of f of x dx. So the general picture for an odd function, if I have something like this and something like this, then from negative a to a, I'll always have the same amount of area above the x-axis as I have below the x-axis. This is if f is odd. And since there's the same amount above and below, we'll always get 0. The picture for f of x being even, it's a nice example of an even function. If I wanted to measure the area from, like, here, call this negative a and this a, then the area here and here is the same as the area here and here. So I could, right? So the area to the left here is the same as the area to the right here. So I could have just computed the area on the right and doubled it. Okay. So I'll leave it just with these pictures. This is a theorem that's good to know because it will allow you to calculate some integrals very, very fast. Even though we don't have the tools to calculate this integral right now, we could write it as a Riemann sum, but we wouldn't be able to evaluate the Riemann sum because how the hell would you with the sine function in there? Even though we can't do that directly, we know that the integral is 0 by symmetry. And sometimes you can use that same symmetry to help with an integral of an even function. So this theorem is something that you should remember. This is a 0. So in the even function, I could have, instead of going from negative a to a, I could have just taken this stuff and doubled it, right? Because this doubled is the same as both of these together by symmetry. Okay. So yeah, Angelica, the bottom limit on the last integral here is 0. Basic rules for definite integrals. Turns out they work for indefinite integrals, so I'll put definite in parentheses. Rules for integrals. They're the same as the rules for sums. So the integral from a to b of f of x plus g of x dx, this is equal to the integral from a to b of f of x dx plus the integral from a to b of g of x dx. And if this were a minus instead, then this would be a minus instead. Also, the integral from a to b of some constant k times f of x dx, the constant k can pop out. So that's k times the integral from a to b of f of x dx for any constant k. So integrals, you can split them up over addition and subtraction, and you can pop out constant multiples, only constants. If k is not a constant, you cannot do this. These two are usually referred to as linearity. This says that the integral, just like the derivative is linear, so is the integral, right? Remember, derivatives, you can split up over addition and subtraction, pop out constant multiples. Same shit works for integrals. These are called linear operators in general, and operator theory is a big deal in mathematics, especially in physics. Another fun rule, if C is a real number, then the integral from a to c of f of x dx plus the integral from c to b of f of x dx is equal to the integral from a to b of f of x dx. And the way we normally think about this is if c is in between a and b. So you can take your integral from a to c, and then your integral from c to b, so the integral from a to c is this guy, this area. The integral from c to b is this guy, this area. And if you add those up, you get the area all the way from a to b. This can be tricky and fun. And there's another one kind of like this. Says, so this isn't rule 1 up here, rule 2 here, rule 3 here, rule 4 here. Says that the integral from a to b of f of x dx is the negative of the integral from b to a of f of x dx. So if you want to, for whatever reason, flip the bounds, then you pop out a negative. So if you want to switch a and b, and there might be reasons for you to do that, you can. Just remember that it pops out a negative. So these 4 rules are the basic rules you need to solve fun problems involving definite integrals, to exploit symmetry, and those sort of things. Make sure I'm not missing anything. Oh, comparisons. Yeah, we should do that. Linearity. Oh, constants, yeah. Go from a to a is 0, okay, yeah. So 2 more little rules. The integral from a to a of some function is always 0. So you're asking what's the area between some number and that same number? That's always 0. So this is an a up here, and this is an a down here. If you integrate from 1 to 1, or 2 to 2, or -5 to -5, some function, there's no width there. So you always get 0. And then kind of similar to 5, another simple one is that if you integrate from a to b, some constant, that's that constant times b minus a. And again, this is for any constant k. There's a little picture that goes along with rule 6 also. Your constant function is just a horizontal line. So if I'm looking from a to b, that area is just the area of this rectangle whose height is k and whose length is b minus a. So these 6 rules kind of give you all the stuff that you need to have fun with definite integrals. split up over addition and subtraction. You can pop out constant multiples. You can split up over a number in the middle. If you reverse orientation, if you flip the bounds of the integral, these numbers a and b, we call these bounds of integration. If you flip the bounds, a negative pops out. If you integrate any function from one place to that same place, like integral from 1 to 1, you're asking what's the area underneath a point? Since that width is 0, the area is 0. And kind of analogous to that, if you integrate a constant function, then you're asking what's the area of a rectangle? Well, we know how to find the areas of a rectangle. You multiply the height times the width. Everybody got these in their notes? Any questions about any of these, or what they say, or why they say them, or why they're true? Okay, then I think we're going to have to stop here for today. I also believe that we've covered pretty much everything that you need for your homework. So there's lots of fun problems about finding areas where you're going to compute a definite integral using geometry. Another one where you're using geometry. Here you're going to use the linearity properties. Here you're going to draw the graph and again use geometry. Here you're going to use these rules that I gave you, the rules 1 through 6, that sort of stuff. Here I would recommend drawing the graph. Here you're going to have to think quite hard. Number 23 is not obvious. So when you get to this, take a deep breath. If you're in a bad mood because the rest of the problems were a slog and they're making you pissed off, stop and come back to it. Number 23 is a great problem to get you ready for what we're going to be talking about next week, which is the fundamental theorem of calculus. Is there anything else in here that I should warn you about before I let you go for today? I don't think so, man. So the practice with summation stuff, we can do another one of these problems at the start of class next time. And then we're going to start getting ready for FTC. Krishna asked a good question privately in chat that I'd like to address to everybody here. When is the next test going to be? Test 3? So because we're so crunched for time, here's my plan. Exam 3 is going to be a little bit more like a project. It's going to be a take-home test. So I've done this in the past in my in-person classes. If I'm a little bit short on time, use the last exam as a take-home test. I'm okay doing that here. So I will explain to you exactly how exam 3 is going to work next week. But basically, exam 3 is going to be a take-home test. So I will send out a PDF of the exam. You will write up nice, neat solutions and submit them on Canvas. And I will grade them like that. So exam 3, I will give you on Friday of next week, and it will be due on the day of the final. So it's going to be a take-home test that you will do on your own, and you will submit the questions to me on the day of the final exam. Okay, so we'll talk more about that next week. But don't panic, it's not going to be a timed, proctored thing like we've been doing for our other midterms. It'll be a take-home, and you'll have a few days to do it. Okay? All right, so I got to leave it here for today. If you have any other questions, you want to talk more about these things, come see me in office hours from 1 to 2 this afternoon. Otherwise, just keep working on this homework, try to get comfy with the notation and the rules that we discussed in class today, and I will see you guys on Friday.